Hi everyone, my name is Emily Black, and I'm going to be presenting Leaving Out Unfairness, which is joint work between myself and Matt Fredrikson at Carnegie Mellon University. As an overview, Leaving Out Unfairness draws together the fields of model stability and fairness by showing how the instability of deep models can lead to fairness concerns through the inconsistency of predictions between models with similar training sets. In contrast to statistical and other group or outcome-based fairness notions, Leaving Out Unfairness draws attention to the need for a fair procedure in obtaining outputs from machine learning algorithms. And as we'll show, Leaving Out Unfairness is pretty prevalent in deep models, so it may be one more thing that we need to think about before we deploy deep models in high-stakes contexts. But let's ground our conversation about Leaving Out Unfairness in an example. Suppose you need a loan, and you apply for this loan at a bank that uses a machine learning algorithm to determine your creditworthiness. So it takes inputs like your credit history, income, maybe your age, and some other stuff to determine whether or not that bank wants to give you a loan. And this model is created by being trained on some people who applied for a loan to this bank before you, and whose outcome on whether or not they repaid their loan or defaulted is already known. Now, suppose whether or not you get accepted depends on whether or not one unrelated person's loan application ends up in that model's training set. That's to say, with all other variables being kept the same, your application, the type of model used, the rest of the training set, if that one other person is in the training set when the model is trained, you get your loan. And if that one other person isn't in the training set, then you don't get your loan. Specifically, let's consider an example taken from an outcome of our experiment on the adult data set, which predicts income above or below $50,000, but let's just assume it was predicting creditworthiness. So consider this 51-year-old woman. She's college educated and self-employed. She's applying for a loan here on the left. Now, if some 39-year-old man in the service industry who finished 11th grade is in the data set, then she gets her loan confidently. So here the model's confidence is 0.87. Model confidence is on a score from 0 to 1. So a score of 0.87 means that the model is really sure this woman should be getting a loan. However, if this man is not in the training set, then she doesn't get her loan. Intuitively, this behavior feels unfair because the model's decision is arbitrary in that it's sensitive to a random detail, this man's presence in the training set, that seems to have nothing to do with whether or not this woman is actually qualified to receive this loan. It seems especially arbitrary given that these people aren't particularly similar to one another, their features are pretty different, and because the model was so confident in its decision, she wasn't a borderline case. Even if you think it's not quite unfair, maybe we can agree that it complicates the ability to give this woman an explanation on her rejection in the case that the bank uses the model where she's rejected. Why was she rejected? Is it because the man wasn't in the training set? And it may also impede her possibility to have recourse, so change her application in a way that gets her the loan next time. So how does this notion of arbitrariness of decision process fit into the world of fairness in machine learning? A lot of fairness literature focuses on how the outcomes of a particular model are distributed among different demographic groups, like in demographic parity, where we stipulate that positive model outcomes have to be distributed evenly across different groups. Other common notions of fairness require similar treatment across individuals who are similar, again, outcome-based. Now, this is all important, but there are also other ways that models can act unfairly. For example, there can be procedural justice concerns that arise when a model's decision process itself is faulty, which is a separate concern from the distribution of outcomes among groups or individuals. Specifically, the procedure by which a machine learning algorithm reaches its outcome is important to think about from a fairness perspective. And there's been discussion about this fact for a long time in the fairness community and an even longer time in the legal community. For example, through the idea that race, sex, or other protected attributes shouldn't be used as a part of a fair decision process. This idea is referred to fairness through unawareness in fairness in ML literature or anti-classification in the legal setting. There are also stronger notions of this idea, requiring that no input used by an algorithm can even be strongly correlated with race or sex or other sensitive attributes, and this is often referred to as proxy use. However, the unfair behavior in our example from before differs in two important ways. First, it's not tied to any demographic group or attribute, but rather to the logic of the decision process itself. Intuitively, that woman's decision seemed unfair because it was arbitrary, as opposed to reasoned or at least consistent. And secondly, the problem isn't with the decision process of one particular model, but rather with the entire process of reaching a loan decision outcome, including the model creation process itself. This is where we connect the field of fairness with the field of stability. Making a machine learning model requires many small arbitrary decisions. For example, deciding who ends up in the model's training set. We hope that small differences in the training set won't matter and that the resulting models that are created are more or less the same. When this is the case, we say that the model creation process is stable. However, this isn't always the case. Sometimes little changes to the training set can result in noticeable differences in the final model that's created. And when this is the case, we say that a model's creation process, or learning rule, is unstable. This instability becomes a fairness problem when these differences affect model outcomes, so whether or not the woman from our example gets a loan. Specifically, instability in the model creation process can lead to inconsistent outcomes between models with arbitrary differences in their training sets, which can seem unfair as they're arbitrary. So this is what we mean by leave-one-out unfairness. The chance that a person's model outcome can change based on a 1-point difference in the training set. Leave-one-out unfairness points to the procedural fairness problems that arise from an unstable model building process. If a model's decision is changeable based on minute, arbitrary differences in the training set, it may cast doubt on the logic involved in reaching that outcome and the reasonableness of the final outcome itself. And beyond this intuitive unfairness, it also may complicate the ability to provide explanations or opportunities for recourse, as we mentioned earlier. With all of this intuition in mind, how do we define leave-one-out unfairness formally? We define leave-one-out unfairness to measure the probability that a specific person's model outcome will change based on the removal of any individual in the model's training set. Let's go through that again more slowly. Leave-one-out unfairness measures the probability that a specific person, person X, their model outcome, outcome K, will change based on the removal of any individual in the model's training set. See here, we're comparing the outcomes between models trained with and without some point I. And then we take the maximum of these probabilities over any point that you could remove from the training set. So leave-one-out unfairness aims to quantify how individual people subject to model decisions may be affected by model instability, not just the behavior of the model as a whole. Thus, leave-one-out unfairness measures an individual person's possibility of a change in outcome in the context of a specific training set and learning rule. It's not an aggregate measure of the model's behavior, which could hide some people's experience if the model's decision were stable on average, like on most people. Also, it focuses on the consistency of prediction rather than error, as an inconsistent prediction, even if it's wrong, may point to some reason behind the outcome. Finally, and most importantly, it's the worst case over all people in the training set given. That is, it'll find out if the inclusion or removal of any point in the training set can flip your prediction. So model stability is a desirable property that's been studied for a long time. How does leave-one-out unfairness connect to more conventional forms of model stability? In the canonical form of model stability, called leave-one-out stability, we don't want the model to change very much between similar training sets from the perspective of the model's average error on points that were left out. Let's look at the differences between leave-one-out stability and unfairness with the help of this figure. What we've got here is two different models. Models are just functions, so we've drawn them here with these little graphs. The models are trained on training sets that differ in one individual, which we can see here on the left. The model on top, this blue model, is trained with this big gray point in the training set, and the model on the bottom, the dashed line, is trained without the big gray point in the training set. We can see the function values on different points in the application domain. Remember, the x-axis is the input, and the y-axis is what the model outputs. And so the green dots mean that the model got it right on that input, and the crosses mean that the model got it wrong. So there are three main differences between leave-one-out stability and leave-one-out unfairness, stemming from the fact that leave-one-out stability aims to measure the extent to which overall model performance, not individual experiences, are affected by small changes to a model's training set. First, leave-one-out stability is an aggregated measure over the model's behavior on all points in the training set, whereas, as we said before, leave-one-out unfairness concerns the consistency of individual people's predictions. Second, leave-one-out stability focuses on error, while leave-one-out unfairness focuses on consistency of prediction. So we're looking at different things when we're comparing the two different models from before. We can see that so to see what this means in practice, let's look at this figure on the left here. We can see that the two models give different outcomes on the big gray point. However, the error of these two outcomes is the same. So the distance from the true value is the same, and so the error of these two models on this point is the same. Thus, from the perspective of leave-and-out stability, these two models are behaving the same on this big gray point, and so this overall model creation process is stable when you take out this big gray point. However, from the perspective of leave-and-out unfairness, this isn't stable behavior because that big gray point is actually getting a different prediction, even if the error is the same. So while this is okay from the perspective of leave-and-out stability, it's not okay from the perspective of leave-and-out unfairness. Thirdly, and most importantly, leave-and-out stability only tracks the differences between models with a 1-point difference in their training set on the exact point that was left out. See the importance of this point, consider the figure to the left again. See that there are other points in the input distribution that experience a change in prediction when the big gray point is left out of the training set. And they did see a change in error, actually. But leave-and-out stability doesn't pay attention to that. It only looks at the difference in error on the actual big gray point that was left out. Thus, again, this behavior is leave-and-out stable. So these two models are leave-and-out stable in comparison to each other. However, they're not. There is leave-and-out unfairness shown by the differences between these two models because leave-and-out unfairness pays attention to the experience of these other 2 points circled in orange. So leave-and-out stability is a great definition to make sure that models as a whole are stable between different training sets, but it's not a fairness definition. And the differences between leave-and-out stability and leave-and-out unfairness show the way that we adjust our thinking to view instability as a fairness issue. Leave-and-out unfairness also has connections to the field of privacy through differential privacy. Differential privacy is another form of model stability meant to protect the privacy of those in the training set from adversaries seeking personal information. So differential privacy requires, among other things, that the actual model created when any point is in or out of the training set is practically the same everywhere. So it'll do almost the same computation and give almost the same outcome on any possible income point that you come up with, not just realistic points. So what does this mean and how does it differ from leave-and-out unfairness? Let's look at these model functions again, coming from different training sets. Again, the blue line is our original model trained with the gray point, and in this case, the orange line is the model trained without that gray point in the training set. The points are points from the input distribution, and where they land on the functions is their output. In leave-and-out unfairness, we care about how the model behaves on individuals, specifically realistic individuals who may actually appear in the application domain. In other words, individuals who might actually apply for a loan, thinking back to our example. But we don't care about how the models act on other points, in technical terms, points outside the input distribution. That is, it doesn't matter if the model creation procedure or learning rule gives an inconsistent prediction for, say, a 256-year-old man with $40 trillion, because that person doesn't exist. He's not what a probable applicant looks like. So from the perspective of leave-and-out unfairness, it doesn't matter if there are differences between the models that have a 1-point difference in the training set, so long as that difference is never felt by people who are actually in the input distribution. However, in differential privacy, these differences do matter. So see here, like this model has a difference between the orange and the blue on this area that's like not affected by any actual input point, and this doesn't matter from a fairness perspective, but it does matter from a differential privacy perspective. And that's because when you use differential privacy, you assume that there's an adversary trying to steal information about people in the training set. So any difference in the model that's perceivable based on a 1-point change in the training set can be exploited to find out information about that person. So while the differences between the solid blue and orange models are allowed within leave-and-out unfairness, that's not good enough for differential privacy. Instead, this dashed blue line is an example of what would be an allowable difference between models trained on slightly different training sets from the perspective of differential privacy. The model is generally the same almost everywhere, even on the 256-year-old. So differential privacy is a stronger notion of stability than leave-and-out unfairness, which may be good news, both for finding a mitigation technique for leave-and-out unfairness and also for finding a softer alternative to differential privacy. So now that we know what leave-and-out unfairness is, how it connects to common fairness definitions and other stability properties, how much do I need to worry about it in the real world? As it turns out, leave-and-out unfairness really is prevalent in deep models. 3 to 75% of individuals in common machine learning data sets experience leave-and-out unfairness. But before we see that, let me quickly explain my experimental methodology. So what we wanted to see was the correspondence between confidence of prediction and leave out unfairness, and here's how we set out to find that out. We trained a baseline model HS, where S is a randomly sampled training set that we use as a point of comparison. Then we sampled 100 points from this training set S, and we trained 100 leave one out models, that is to say 100 models with 1 point left out from the training set. Then we calculated the differences in predictions between the baseline model and each leave one out model over the entire data set. For every point in the data set, we checked to see if there was a change in prediction between the baseline model and any of the leave one out models. These were the points, if so, these were the points that were experiencing leave one out unfairness. Finally, we plotted the percentage of these points in the data set that were experiencing leave one out unfairness versus the confidence of their prediction in the baseline model. And we got the graphs in our results section. So going back to the substance of our results, how much do we need to worry about leave one out unfairness? And as I said before, it turns out leave one out unfairness is pretty prevalent. So pictured here are the graphs of the percentage of points that experience leave one out unfairness on the y-axis and the confidence in the baseline model on the x-axis for deep and linear models and common machine learning data sets. You'll also notice some other plots on these graphs with more exaggerated leave one out unfairness. These are results for robust models, and we don't have time to cover that here, but if you're interested, please read our paper. As we can see from these graphs, the slope of these lines are close to horizontal, so that means that it's often high confidence points whose decisions can be flipped by arbitrary 1-point changes to the training set, meaning that it's exactly the points that the model purports to be confident about that are experiencing arbitrary decisions, in that they can be changed based on a 1-point difference in the training set. Notably, leave out unfairness didn't seem to depend on the makeup, type, or size of the data sets tested. We have here German credit on the left. Which is a tabular data set, seizure, which is time series, and labeled faces in the wild, which is image, and leave out unfairness was present in all of them. There are even more data sets in the paper. Also, interestingly, leave out unfairness doesn't seem to correlate with the accuracy or generalization error of the models. So models with higher accuracy or lower generalization error could have more points treated leave out unfairly than models with low accuracy and high generalization error. This is surprising given some of the connections between general notions of stability and generalization error. So here's a quick example. This German credit model has an accuracy of 75%, generalization error of 25%, so quite abysmal, and the leave out unfairness, about 7% of the population experience leave out unfairness. Whereas in the labeled faces in the wild model, we have an accuracy of 86%, so that's 11 points better. Generalization area of 5%, which is a fraction of 25%, but the leave out unfairness is 77%, so much, much bigger. So from what we can see here, the extent of leave out unfairness in deep models may be one more aspect to consider before using a deep model that may affect people's lives in the real world, as intuitively, people experiencing leave out unfairness may be experiencing arbitrariness in prediction, which could be unfair, especially in high-stakes situations. So I've shown you here how prevalent leave out unfairness is in deep models, but leave out unfairness is just one way that arbitrary decisions made in the model creation process can propagate down to the outcomes to give inconsistent outcomes. There are so many other random choices that we make during deep model training, from setting our random seed to picking our architecture, that can also lead to inconsistent outcomes. They all have effects, some larger than others, and we have some preliminary experiments in section 6 of our paper, should you care to read it. That's pretty much it for my presentation, but there's so much more to our paper that I couldn't cover. Please read it if you're interested in the connections between leave out unfairness and robustness, extended experimental results over more data sets, connections to individual fairness, proofs for the relationships to leave out stability and differential privacy, case studies of leave out unfairness and facial recognition, or personal finance contexts, and so much more. Thank you so much for your attention. I look forward to hearing your questions. Thanks so much.